Okay, guys, welcome back. So, day number one, the first thing that I want to do today is to be sure that we know some basic concepts that we're going to be using in the future. Remember, our goal is to create software. Our goal is to use libraries and put together components and deploy systems, right? Yes, we need to know some internal components of this box that is the one that is going to provide some learning or intelligence, whatever. But our goal is not going to go inside of that box and try to improve that part. That is computer science oriented thing. But we need to be able to understand the basics, like the engine of a car, because we want to drive the car. We do not want to be a mechanical engineer, right? That is the concept. However, we need to understand how the engine works, because we're going to be using that. So we're going to be sure that we understand some concepts, some ideas, some topics, some things that we're going to be reading online, even in the documentation of the software that we're going to use, the frameworks and the libraries, correct? So concepts, key ideas, and you can help me to describe into details whatever is needed. Number one, I am going to start with the key ideas of the machine learning part. So I am going to be talking the next 20 minutes about computer science topics. Later, you're going to notice another slide focus on software engineering, right? So machine learning, kind of a summary, simplification of something that in computer science you're going to review or can review deep. Number one, the first question that I could ask you is, what is machine learning? Because there are a lot of very fancy concepts, right? Deep learning, artificial intelligence, machine learning, data mining, and more. Help me. Specifically, why this class is about machine learning, not about artificial intelligence? There is any difference? They are the same? What is machine learning? Ideas? Probably I can help you to make a question more specific. Machine learning. Learning is one idea, right? The machine, obviously the computer. Artificial intelligence. Artificial because of the computer, okay, intelligence. What is the difference between learning and intelligence? Is the same? Similar? One is inside of the other? Think about human beings. You are intelligent. You can learn. What is more important? What is more complex? Can you agree with that? Not only for the humans, but also for the computers. Can we agree that intelligence is kind of, whoa? Help me. Two things that make you, humans, intelligent. Two things, or if you can give me three, that make computers intelligent. When you listen the word someone or something is intelligent, what are you expecting from that entity, human or not? Different what?
Different approach in thinking.
Different approaches to do, to solve a problem. So intelligence implies that you can solve problems. But in order for you to solve a problem, you need to learn to solve a problem. Can you agree with me that intelligence implies learning? I mean, learning is just one small part of being intelligent. Just one small part. What could be the second part or another part beside learning? Thinking.
Applying to learn.
let's talk about thinking in order to apply something. You think, what are you going to do? And then you do it. There are more about it, but let me take thinking. Can we agree that thinking is not the same as learning? I mean, I am talking about human beings, not yet about computers. But you can learn something. And if you learn something, hopefully you learn the content of this class, but you learn programming, or you learn software engineering, or whatever. And that is just one signal that you are intelligent, or just one element in your intelligent behavior, right? The other, the thinking, is more complex than the learning. Because to be honest, you can learn something just by memorizing things. Yes, memorization is one way of learning. You can show me that you can do something like your final exam, you learn, but you memorize, which is not the same that thinking. Thinking is more like a rational process in which you learn in a better way, or moreover, can choose or can select the best approach according with the situation. And the best approach is not always the faster or the correct solution. And we're going to talk about it, but being intelligent is about understanding that the correct solution from a point of view could not be the best one to apply. You have an exam tomorrow. You need to study. What about if you have 5 exams tomorrow? The correct approach is to study for the 5 exams. It's going to use a lot of resources. So in that point, you start taking smart decisions and selecting which exam are you going to prepare and which others are you going to do something else. Something else, including asking the instructor to, please, professor, can you change the date? This is a behavior, and it's an intelligent behavior. It's a human being behavior, yes or no? So, learning, intelligence. We're not going to talk here about intelligence. It's kind of so much for us. We're going to talk only about learning, period. Clear. Now, the name is machine learning. Yes, because we're going to talk about learning, not human beings, learning about the machine, learning about the computer. Good. Question in your exam, for sure. I am going to ask you, what is machine learning? Just because it's the first thing that I am explaining to you. Now, to be sure that you remember, I am going to share these slides and you can review it later, but machine learning, one circle inside of artificial intelligence. That is the thing that I am explaining to you. And obviously, artificial intelligence is inside of computer science. There are much more there in computer science than artificial intelligence, but you notice just the connections. Good. Now, obviously, what we're going to be talking here, what you need to know in order to do machine learning, even though we are not going to go into the details, but you're going to notice, it's going to be all those elements and different colors. If you want to go to machine learning from the point of view of computer science, obviously you need to know data science. And I am talking about statistics. And if you're thinking about data mining, you're going to find that there's a small part there that is kind of the intersection of data science with the things that we're going to be doing here. Moreover, there are several different fields. Some of them in the computer science part, some of them in mathematics, some of them more in data. We're not going to cover those things. The only thing that we are going to do here is machine learning. And machine learning, an overview, because what we need to do here is how we put those things, that circle there and the elements inside, together with software engineering, because our goal as a software engineers is to deploy a system. That is our goal, right? Yeah, we need to do this review of learning. We're going to start talking about models. One of the steps of the process of learning is to create a model of the knowledge. We're going to be creating models. I am going to explain that in the following slides. Our approach, what we care is, I want to have a model, period. I want to be able to show that I learned something, but there are always better models. So there are always more things that I can learn. That is not our concern here. We need this space in which whatever we do with machine learning is going to be just one block of several other blocks. And this is our system, and we want to create the system. And our concern is how this thing is going to be connected with other things. Remember, software engineering. And I am going to talk more about it, but components. Good? Clear? Now, machine learning, the definition, this guy. This is one of the fathers of machine learning as a science. Why I am showing you this? Number one, notice the dates. This is very old thing. Why? If this idea is from the 70s, why until today, 2022, is kind of the top of the list in terms of relevance, right? Why? Why machine learning or artificial intelligence or whatever was not like today in the 90s or the 80s or 20 years ago? What is the thing that changed that we can do today, but it was very hard to do 20, 40 years ago?
The hardware is powerful enough?
Yes. The definition is very old. The ideas, the things that we're going to review are very old, are in the mathematical field. And this is the date for the computer science part, the implementation of those ideas in a computer. But the ideas itself are older than that. The mathematical part on paper. Knowing how to do the things have been there for a long time. Put those things in the computer have been there for a long time. The issue is the hardware. The hardware. Why the hardware? One thing, learning. I am going to go into the details of this, but I want you to be aware. When we talk about learning in the computer, a big component of that learning is the following. And let me ask you, you're going to learn something. You're going to learn to drive a car, or you're going to learn to do programming. What do you do to learn?
You familiarize yourself with something through experience and expand your knowledge through it by going beyond the limits of your own knowledge.
Can I summarize that with you collect data? I mean, there are better ways to put that in a paragraph, but you collect data, right? For whatever, you need data. I give you a class of Java programming or C++ programming. So I give you the data, the words in Java and the grammatical rules of Java. You have the data. But is enough for learning? What is the next step that you follow to learn?
Processing the data.
Information and memorize it.
One thing.
We have to train ourselves.
What?
We have to train ourselves. And we have to test if we have done correctly.
Yes. I am going to put those ideas into words, and you can help me if they summarize what you describe. You're going to When you learn programming, I give you the information. Then you start doing programs. Right? I mean, somehow you apply the information, but you're learning to drive a car. You apply the information somehow. Don't worry, I am going to tell you more about what that means in terms of the computers. I am talking right now about human beings. You have the information. Step number 2, you try to figure out something, some kind of process, or some kind of what can I do with this, right? And then you figure out this process or this, what can I do, or these steps, and you apply them. If I teach you how to drive a car, that will be the best example, is like, okay, this is this control, this control, this control, your feet, your hands, and then you try to do it. You try to do it not with the process that I have. You try to do it with the process that you get from the information that I give you. That could be correct or not, but with the information, you create kind of a model and you apply your model. What could happen is going to happen that you're going to fail. Learning is always connected with failing, with making mistakes. People do not learn the first time, machines either. We learn, create a model, apply the model, make mistakes, fix the mistakes. I am going to be using a lot this word, model, a lot. I just make the connection between, okay, model and the process, the thing that I am going to do. Help me, what is a model? You are software engineers, and I am sure that you remember UML. You remember that the M is something related with modeling. So you know what is a model.
Way of representing an idea or problem.
Okay, number 1, very important. We're going to be talking about models. And models are representations. Representations of what? Beyond the data.
Real life phenomena.
The what?
Real life phenomena.
I am going to use that one. That is true. But for us, thinking about as a software engineer, what we represent is something that I am going to do. I am going to use the word process, even though what I am thinking is a model is a class diagram. And if you think about the class diagram, what is representing is not data. It's representing what are you going to do in order to create that software. Because the diagram, the model, is telling you what to do, which classes to create and how to connect those classes. And I am using that example just because it's familiar to you, right? The idea is that in machine learning, learning is about collecting data and doing something to, from that data, create a model of some kind of process. I'm going to go back to my example of driving the car. Collecting data is listen to me or listen to your friend or whatever that is teaching you how to drive the car, and your friend is going to tell you a lot of information. And what your brain is doing is try to create this model, this representation of not the data that you're collecting, because you're not creating this kind of diagram of the data and the words of your friend. What you're trying to figure out is the process that you're going to follow when you need to solve the problem. When you are alone in front of the car, yes or no? Somehow from the data, you're going to figure out a process, and that process needs to be represented somehow in your brain. And that is what you're doing. Clear? Okay, now I need to talk about the machines. What could be this model inside of a computer if what we want in machine learning is that the computer learn to do something that the computer have never done before. We need to create a model. And what we are going to create, what is going to be that model inside of the computer? It's going to be a draw. It's going to be a document with a lot of instructions, like a program. What? An algorithm. Yes, but we need to go more specifically. If we talk about algorithms, we're talking about programs, right? Because a program in Java, for instance, is the translation of an algorithm to source code in a particular language. So something that I want to be clear, machine learning is not going to create a program. It's not going to create source code, right? That is not the approach. What are we going to create? A model, but what is going to be that model?
Yeah, I think model is just like a formula to give out an output.
Yes. Let me be clear. This model for machine learning purposes is going to be an equation. Guys, I am going to remove all the romantic thing about the artificial intelligence and machine learning and so on. I am going to remove all the fancy things. Machine learning is all about giving data to the computer and asking the computer to figure out an equation from that data. Equation. It could be as complex as you want. I mean, I am not talking just about a quadratic equation. It could be something else, something more. We're going to review things. At the end, it's just as simple as asking the computer, create an equation that connects this data, and the equation represents a process that I could follow in order to show my user that I just learned how to do something. Clear. Now, I am simplifying things. I am telling you that this is one equation. It could be more. At the end, equations. Clear? Now, let me simplify things more. Thinking about equations. Depending on the approach that we follow, if we're going to use neural networks, the equations are going to be in some particular category. If we're going to use regression or support vector machines or whatever, each of the process, each of the different approaches are going to create a particular kind of equation. All of them similar. Can you tell me what is the element inside of one equation that is really important, relevant? What makes one different to others? Because equation x, y is equal to x plus 1. It's an equation, right? Don't worry, it's not going to be any relevant, but in this equation, this guy or this guy are important. It's your input and your output. You know math, right? They are irrelevant. Why they are irrelevant? Because this is my input. All this data are going to become those. Think about an Excel spreadsheet. What I am telling you is each column is going to be 1x. Whatever, you can think about x exponent something or x1, x2, x3. Each column is going to become one of these inputs. And this y is the output that you are searching for. Several of these, one of these. That is the general idea for any equation. Any equation that you look in your math book, doesn't matter that you're looking algebra or calculus, advanced calculus, it's going to be something like this. It's a function in which you are searching for the value in one variable. This value is the action that you want to follow, to implement, and this is your input. Tell me, in this equation, which elements are important, relevant, key? And it's not the Y, it's not the X. Those are just inputs and outputs.
How they are related.
The operators are important, and the operator is something that we're going to put there depending of the method that we select. If we select, again, neural networks, if we select support virtual machine or whatever, the operators are going to be there. The connection between the inputs and the outputs are going to be there, just because the selection that we do of the approach. What is important? The only thing that is important the coefficients of each variable, the inputs, and one extra coefficient that is alone without the input. Do you remember in math, what do you do with these numbers? What? Do you remember that in math, in some point, when you learn how to solve equations, these numbers were important and you put them? You mentioned that.
MX plus C.
And what?
MX plus C.
Yes, could be one of the approaches. But do you remember that these, in some point, become a matrix? I am talking about your background in math. If this do not ring the bell, just believe me. When you create an equation, when you try to solve an equation, the important part of the equations are the coefficients. And what you do with the coefficients are store those coefficients in arrays. Well, have a different name in math, but for computer science, arrays. Arrays. The only thing that we need to do for learning is to take the data, try to figure out an equation, and in particular, we are not going to figure out the equation. We need to figure out the coefficients for an equation that is predefined. Period. Really? The only thing that I need to do is to find these numbers, and that is going to be intelligence. Yeah, learning. Really?
Don't we need to figure out the degree of the equation?
That is going to be another part. It could be another number there. I need to talk about it. But that is something that we figure out before I start learning. Let me be clear. The first thing that we're going to do is to select the approach that we're going to follow. That approach is going to tell us the shape of the equation. Then what we're going to do is to figure out the best specific implementation of the approach to follow depending on the problem. In that thing, we're going to figure out exponent operators and so on, but we're going to do that before the computer starts working. When we ask the computer to start working, to start learning, to start processing the data, what the computer is going to do is take that, the data, and look for the numbers. Done. You know what happened? Going back to the hardware, how easy or how hard is for the computer to do things that involve this kind of representation? You know what is the good news? That in order to process this, arrays, matrix, vectors, some years ago, doing this with only one CPU, you know, time consuming. So thinking about in the 50s, 60s, and so on, to create something intelligent, yeah, what possible? You can do it in the lab. Oh, it's intelligent, great, perfect, wonderful. what is the point? How many CPUs in your laptop? Several more. You know what? More CPUs, faster to process this. Forget about the CPUs. You know what? The GPUs are not as powerful as the CPUs. You cannot just put a GPU in your computer because you need a CPU for several different things. But one thing that the GPUs are very good at, graphics. No, this. No, but the GPUs are for graphics. Guys, graphics are this. So how many GPUs do we have in your laptop? Hopefully it's one, but you can find more. Not in your laptop, but we can move, for instance, to the cloud. You can get a free account in a computer or even in the high performance computer here in ASU. And how many GPUs can you get? More than one, for sure. You know what? The speed to process matrix operators with these guys or these guys is fast. Oh, very fast. Very fast, which means we can increase the amount of data. Again, remember that we start here with the data in order to get an equation, and in order to get the equation, we're going to do something with these guys. I am going to describe more details. We need to process these guys. We need to do operations. Again, I am going to go to the details, but the fact that we now have better hardware means that we can process more data in the same amount of time. Remember, we want the computer to learn, but learning is something that should happen in a predefined amount of time. I mean, you can learn programming, but if you do not learn programming in one semester, well, you do not want to be taking CSI 110 for years, right? Stop trying. Similar with the computer, please. Now, let me be clear. We need these guys used for learning, used for getting a model. What happens when you have the model? What happens when you learn to do something? Every single time that you're going to do that something, you need to create a model again or not? Or is one-time thing? That is clear, right? Again, with my example of the car, it's like you need your friend to teach you how to drive the car. And you're going to create a model about how to do it. And you're going to try to drive the car, and maybe you're going to make mistakes, and your friend is going to give you more information. And in some point, you're going to have a model, an equation, not an equation exactly in your brain, but that is the idea. That is your model, your representation about how to do that task, about what are the inputs, people, cars, lights, and what is going to be your output. Stop or move. When you have a model, good enough, your decision, you're going to start following that model every single day in your life when you take a car. You can stop there. Or you can continue learning, reinforce your model. But this is not mandatory. You have the model, you can do the task, you can continue driving back for the rest of your life. Right? And you know what? When we are done with these two things, that is the moment in which we need this. And that is something that I described in the previous lecture. Here, when we have the model, when we have learned how to do something, in that point, computer science is happy. We are done. We have the model. We have the equation. The application of the equation is secondary. For you software engineers, no, the application of the equation is not secondary. The application of the equation is just one box in a collection of boxes. Clear? Okay. Now, Can you agree with me in the following things? I am going to go deep in this model in a few slides, but just to stop with the concept. Machine learning, artificial intelligence. My first column here, artificial intelligence. My second column here, features of machine learning. Can you agree in what is there? Can you agree that if we mention artificial intelligence, we are talking about learning, reasoning, and self-correction, mostly, not the only elements, but three important elements. On the other hand, when we talk about machine learning, it uses learning and correction. We remove reasoning, the one that you mentioned before. I just put here the definition of what you mentioned. Moreover, when we are talking about artificial intelligence, we are talking about different kind of data. I didn't mention here what I call data. But the important thing that I want to point out is when you work with machine learning, usually, most of the time, learning implies that we have data that is somehow structured. Data that somehow follow a pattern, like an Excel spreadsheet, like columns and rows. Is a total 100% structured data. We know each of the parts of the data. It could be an HTML file. It could be a JSON file. It could be an Excel spreadsheet. It could be comma-separated values. There is a structure there. We need that structure to learn. Artificial intelligence, and we're going to kind of cover an introduction, is about learning, even if I have data without having an idea of the structure of the data. Makes sense? Again, it's about more complex learning, and it's about reasoning and other things. Good? So why I put those things there? I need you to remember, we're going to use data. Our data needs at least a semi-structured pattern. Some kind of a structure, some kind of format, if you want. Clear? Why? Because the equations that we're going to create, the input that we're going to use, somehow we need to explain how to match them. And it's easy to do it if we have a pattern. Machine learning, easy compared with artificial intelligence. Now, just concepts. Now, we're at the center, machine learning. But I am sure that you have learned, or at least read or listen about all that works there. And somehow the picture is going to show you the important ones and things that could be more less common depending on your previous experience. Why I put this draw? Things that I want you to know. When we talk about machine learning, there are two kinds of learning that we are going to be reviewing here. We have supervised learning and unsupervised learning. Tell me, what is the difference between supervised and unsupervised? And yes, I know that there are more elements there. I am going to start with this supervised and unsupervised. What is the difference between supervised or not? What?
Data is available for supervised.
Having available what?
There is a developer input prompt in the supervised learning.
Okay.
Developer input is required for supervised learning.
Developer input, yes. Let me explain this, taking those two things. You're learning here. You're learning when you take this class or any other class is supervised or unsupervised? Supervised, yes. Why?
It's labeled, data is labeled. It is features that you pick on, and then you learn from the features that are already there.
Okay, you are right. There is one thing that is the reason because it's supervised. You are right in terms of what you are mentioning. One important thing that I want you to have in your mind. The only reason because the learning is supervised is because I have the answers. It's because when you're going to do a homework, a quiz, or an exam, I am asking you for answers, but I already have the answers. So when we talk about supervised, it's because the answers exist. I am asking you to solve a problem that I have the answers. The only thing that I'm going to do with you is to compare if your answers match my answers. When we talk about supervised, is the answers already exist. So you can think about this idea of the data that is going to be the input for anything that is supervised learning. The data include the inputs and also the values for this guy, that is my output. If you have inputs and outputs, and you give that inputs and output to the computer, what you're doing is asking the computer to learn in a supervised way. Why? Because these are the answers, these are the inputs, figure out the process. Okay, you can apply your process and you can compare whatever your process give you with the answers that I already give you. Make sense? Clear? You are oversimplifying things. Yes, I am oversimplifying things because that is what I need you to know to move forward to software engineering. There are more things that you can learn in computer science. What do you think is unsupervised?
We're only giving X, not Y.
Exactly. From a mathematical point of view, you do not have these values. You do not have the answers. Think about unsupervised learning, more like research. I can be here and trying to teach you how to program a quantum computer. And I have no idea how to program a quantum computer. Well, I have some ideas. Here is the information that I have. But we together can figure out what to do. I do not have the answer. So we're going to try to do something. And hopefully that gives us something that we expect, maybe not. Let's check. But there are no answers. I cannot supervise your work because I do not have the answers to give to you. And then you can compare. It's like together, this is the input, the X, and let's see what happened. Clear? Supervised learning, unsupervised learning. Something that I am going to be doing the rest of the semester is asking you when we start working with something, hey, guys, this is supervised or this is unsupervised? And it's going to be in your exam also. So hopefully you remember what was the definition. Clear. Good. Now, in each of the two approaches, supervised and unsupervised, there are different process to follow, different things to do, different approaches in letters without circles. However, the most common things that we do in machine learning for supervised learning is going to be classification or regression. I am giving you concepts that you're going to read later. Classification. Can you explain to me classification from the point of view of learning? Imagine that I give you an Excel. And imagine that in that Excel, I give you all the grades of your classmates or one of my classes from the previous semester. All the grades, quizzes, exams, etc. Moreover, imagine that I give you also the data of the attendance to the class. If they attend or not, every single class. And at the end, in the last column, I cannot tell you the final grade of the student, but I can tell you if the student passed or not. That is the data. What I would like you to learn, to figure out, is what if you, in some point, are going to have grades for the same activities, and I'm going to have attendance to the similar or same classes. Can you tell me if these new students or yourselves are going to be the category of passing or not my class. It's kind of prediction, right? The name of prediction here is classification. Prediction is kind of too esoteric. So classification. If you have the data about what happened before, tell me what is going to happen in the future. Supervised. Did you notice why I supervised? Because I give you the input, but also I give you the output, pass or not, input and output, figure out the model, an equation. And with that equation, if I give you new input, new X, you give me the output, the Y, pass or not, binary output. Good? Unsupervised. There are going to be several things. I am going to mention one just to give you the example that is the opposite to the supervised one. The most common thing that we're going to do in unsupervised learning, one of the most common, clustering. Another fancy word that I need you to remember. What is clustering?
Bunch of data.
I like that idea. Put things together, create clusters. Did you notice that this is the unsupervised part, right? What if I give you the same information that before, the grades and the attendance of my students in the previous classes, but I do not tell you if they pass or not. I just give you the inputs, the information, right? And what I am going to ask you, because it's unsupervised learning, I am not asking you to figure out the question about passing or not passing. You do not have that information. For you, pass or not do not exist. What I am going to give you is here, those are the grades. Can you figure out like different categories for my students? It's like, can you read the data? And it's like, okay, look like there is a category here about people that always get 100. Okay, there is another category here about people that always get zeros. Okay, there is a category here with people that never went to the class but get 100s in every single homework. Okay, another group here with the opposite. I don't know. Is you're going to check the data and try to figure out these different groups, clusters. Why? Because later you can come to me and tell me, Professor, we have these 5 categories of your students. You have good students, bad students, and 3 in the between. Oh, wow, very smart. Clusters. Clear. Supervised, unsupervised. A good example of supervised classification. A good example of unsupervised clustering. Clear. Okay, now, the best one. Some people put in a separate category 2 things that we need to review, maybe at the end. The most important ones at the top, supervised and unsupervised. That is the things that we're going to be working the most. But then, reinforcement learning, and deep learning. Very fancy names. Let's start with the easy one, reinforced learning. What is this word?
Trial and error.
What?
Trial and error.
Let me give you the example. Supervised and unsupervised is about 2 steps. Step number 1, you have the information, you create a model, you test your model, and in some point, you are happy with the model. In some point, it's like, okay, this is my equation, clear. And then you move the equation to the system, and the system is going to be using that equation. Done. Did you notice the separation of the 2 things? Number 1 is learning, and number 2 is applying what you learn in production. Okay, but doing the model supervised or unsupervised, whatever, doesn't matter. You do the model, then apply the model. Can you agree with me that something that human beings do is you learn to drive, you have your model about how to drive, but every single time that you go outside and drive your car, somehow you learn something new? In terms of the computer, that means that even though you are here applying the model, done with this learning process, can you put feedback? And in real time, create another model, improve your model. But remember, the only way to improve your model is that here in real time, you are collecting more data. And with the new data, what you want to do is reinforce your model, improve your model. Make sense? Okay.
This feedback thing can happen in supervised learning as well, right?
Yeah.
So is that classified reinforcement?
Well, the more important thing is the way that we do this is going to change a little bit. And the process that we're going to follow are going to be a little bit different. It's not just a loop to do again whatever we have here in supervisors or unsupervised. It's going to be about a different way to found this equation that is going to consider not only the input data, but in some point, it's going to consider this feedback thing that are not equal to a new data set or the full previous data set with more data. It's not like redo everything, but it's just like about, hey, I already have the model, I already have the coefficients, and now I want to kind of improve a little bit this. And it's going to be a special way to do it. And that special way to do it, that process or that methods that we have are put together in this category that is very fancy to name over reinforcement.
And so does increasing the data always enhances the model, or can it degrade the model as well?
Whatever, it's going to change the model. So it's going to change, and technically to improve, not always improve, but we need to talk about it. It's all about testing. Now, that is kind of easy. Like, okay, we're talking about new things that we can do, and it's like use feedback for the model. Fancy, good. The most fancy keyword that you're going to learn and you're going to use, deep learning. Anyone, can you tell me about what is deep learning? Because sometimes, again, it's like, oh, it's the same as artificial intelligence. Oh, well, it's the same as machine learning. No, it's not. It's just one category of the different ways to do learning. Deep learning. Oh, learning we already described. Deep. What is the meaning of deep?
Depth of the node.
What?
Depth of the node.
Again, sorry.
Depth of the node.
Like what?
Basically, sometimes you only use few number of nodes, but in deep learning we use multiple depth.
Nodes. Did you notice that we just moved to a new concept about nodes? Nodes of.
Layers like node.
Okay, notice that we are talking about layers.
I mean, output to one layer is input to another layer, and that's why it is deep connected type of learning.
Have you noticed that they are talking about neural networks? Layers and nodes? Yeah, neural networks. Not any kind of neural network. In particular, neural network with more than one layer in the middle. When you have neural networks, or any other approach in which you have a hierarchical approach, like a tree in data structure. Remember the tree was kind of great. The closest thing that we have to a tree, the analogy, they are not connected, but just to use an analogy. The power of trees in data structures is like talking about the power that we're going to have in this approach called neural networks. In particular, because one thing, we can put layers there. And layers are going to create something like you described This is a layer. Another layer. More layers here, more deep the learning. Really, deep learning, because, yeah. But, yeah.
Does each layer represent an equation?
Okay, very good question. There is an equation here that is the same equation here, that is the same equation here, that is the same equation here and here. For our purposes, you have one equation, the same equation inside of each of the nodes. Fancy name for the node, the neuron. The thing that is going to be different is the coefficients for this equation and the coefficients for this, and for this are not going to be the same, do not need to be the same. It's the same equation. All of them can be something like this, but each of them is going to have its own coefficients. The theoretical background is more layers, coefficients, 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 coefficients. And you can imagine that when you put here at the end, this result is the result of a more complex equation that use one of these or even the combination of this. And I am going to give you an example, but the point is deep learning, more equations, period. Oversimplification, yes, very oversimplified, but hope you get the idea.
Simple classification. I really have to make a model.
Very good thing. And my best answer could be, what did you use if I asked you to code this table? Did you use the same tool to code a piece of bread? Different tools. Why? If the saw is so powerful. Same idea. What is going to happen if you use the saw with the bread? You're going to do a mess. What is going to happen if you use neural networks, this powerful tool, with a problem that can be solved like use regression? It's going to give you bad results. Really? Are you telling me that this powerful tool is going to give me more errors than the regression? Yes, that is going to happen. The key idea that you need to learn, and the reason because you never learn neural networks, you learn more, is you need to learn how to select the correct tool. Hopefully that is something that answers the question. You're going to notice what we're going to be doing, and you're going to notice that for each different thing that we're going to do, there is kind of one tool that is the best one for a particular approach or problem. Let me give you an example. You have a picture. In the picture, you want to recognize the elements of the picture. Okay, two things. I can ask you to recognize a human face. A human face, the eyes, and so on. Which one is the best tool for that? You do not need to know it, but support SVMs, support vector machine. We're going to talk about it. You're going to play with that. However, if you want to recognize objects in the picture, like you want to recognize the dog, the cat, the people, the bicycle, and so on, like driving a car and different things, neural network. Why didn't you use the neural network with recognizing the face? Recognizing the face is too easy. And neural networks start complaining about things being too easy. Again, my expectation is that you play with that and you're going to notice this. Good? Okay, now, more. Hopefully we have the opportunity to play with at least one of them in each of those 4 categories. Let's see what happens now. I am talking about neural networks. You mentioned layers and you mentioned nodes. Therefore, I am jumping to my slides about that part in particular. I want to explain you how these things work. And I am sure that after I describe the different things, the one that calls your attention is deep learning, because it's kind of the fancy word outside. Moreover, if I mention neural networks, I am sure that you listened about neural networks before, right? And the first thing that I could ask you is, what is a neural network? You already mentioned these nodes, the neurons, and you mentioned layers, and I put this picture there that I am going to create later there. What is a neural network? If you read the definition online or in your books, what the people tell you that is a neural network?
There's a network of nodes
Mhm.
where each node represents the same equation but with different coefficients, and data flows from one end to the other end.
Yeah, that is the correct definition. But that is not the definition that you put in a web page. That is not the definition that you put in the marketing. That is correct. A neural network is a graph. You know graphs, right? And the only thing that you have is inside of the graph an equation, the same equation inside of all the nodes. But that doesn't sell, that doesn't make marketing. Marketing is a neural network, is a representation of the neurons in your brain, but in the computer. No, it's just a graph with equations. Really? Yeah, really. A node, and inside you have an equation, and any equation is a function, and the function have inputs and outputs. Yes? Okay, now, if we think about the function that we're going to use or that we're going to have, or if I ask you to implement this from scratch and you're software engineers, you know what? Remember that Excel table that I mentioned before? And remember that before I told you that each of the columns is going to be like an input? And maybe one column, the last one is the result, right? Like the pass or fail the class. What I am telling you is you're going to have this class node or maybe neuron. And each of the inputs is going to be one of these X in the equation. And we're going to consider an X every single column in this Excel data sheet. What about the output? We don't care about the output yet. I do not need the output, not yet. The input for the node, the columns. Can you imagine that more columns we have, more input can go inside of this guy? What can you do if there are too much? Some neurons can have some inputs and another neurons can have another inputs. Think about a picture. You can put every single pixel inside of one, or you can split the picture in 4 or 16 or whatever, and use different neurons for different parts of the picture. We need to talk about that later, but it's the approach. They are going to go inside, and we need an output. The output, an equation. What is the simple equation that we can have? What is the simplest way in which we can put together all the inputs? The simple equation, addition. Why? Because the computer, remember our GPUs and CPUs? What operation those GPUs and CPUs or whatever can do very well? Multiplication and addition. Period. And what about division and subtraction? They are special cases of multiplication and addition. Period. What about all the other operations? They are special cases of multiplication and addition. So a neural network is an equation that starting is going to add all the inputs. It's going to be an equation x1 plus x2 plus x3 plus x4 plus whatever. Really? Yeah, really. What else? Well, use addition could be so complicated, so simple. Let's add something else. Something else. My result is equal to the addition of things. You know what is the problem here? That the result that we're going to get, the smallest value and the highest value, we have no idea what are going to be. If I ask you for only addition, small value and highest value, we do not have it. Do you think that we're going to need it? Could be a good idea to have knowledge of which is going to be the small value and the highest value. Hopefully you agree with me. Yes. Why? Because of the computer. Do you remember the data types? Do you remember that the computer cannot handle infinity to the infinity plus and to the infinity minus? There are some limits to what the computer can do. Whatever, it could be very fancy. It could be very useful for the human, and it could solve the problem of the computer. If we can be sure that whatever is going to be the result of this equation, and therefore the values for this guy can be in some kind of higher minimum and maximum, right? Would you like to have like the minimum 0 and the maximum 1? Or would you like to have the minimum -1 and the maximum 1? Can you agree with me that that is fancy? That is great. So the next question could be, what can you do in order to be sure that doesn't matter what is the output, that output is always a value between, let's say, 0 and 1? Because that is the problem, right? It's not a computer science problem. It's not a software engineering problem. It's a mathematical problem. Your inputs, you are going to add everything, and I am asking you to tell me a result, and I am asking you that the result is 0, the minimum, 1, the maximum. You do not need to be experts in math, but maybe you know this guy. If not, you can search for this small guy online, very important guy. In fact, this is the guy that made a neuron. Well, not the only one, but the first one that made the neuron really something that could be useful as a neuron. Because now we have something that is going to be 0 or 1. And the mapping with the neurons in your brain is on or off or something in the middle, right? Can you agree with me? And this is something that you can play. That doesn't matter what is the result here, what is the number that I put in the X. If you apply the equation, the output, the result is always going to be in this part. Again, you do not need to understand the background. The only thing that I ask you is play with the values. Doesn't matter if you put 100 there or 1,000 or 1 or put a number. And your result is going to be around there. But more important, did you notice that it's going to try to make this change kind of instead of having some kind of line, instead of having use any value the same, any possibility can be there. Something that happened with the equation is you're going to have something more close to this. What is the difference? That small values are going to keep being kind of 0. Biggest values are going to be keep like 1s. It's going to be kind of a separation of things. It's not like every single part is equally thing is this or this or this. The first step for a decision, yes, no, maybe. 3 categories versus all the values. Why that is important? Don't worry, I'm going to show you. So far, okay. So inputs, addition of the inputs, And this fancy equation that is going to help us to keep the output in a particular range of values. Normalization.
But why is there a need of such a complicated function?
Sorry, what?
Why is there a need of such a complicated bounded function? Why it can't be a simple trigonometric function? We know that tan inverse lies between -1 and 1.
It could be, I mean, this one is just one example of one equation that is used that is very common, but it's not the only one. And the one thing that we're going to do later, and the reason because I am mentioning this is I am going to give you a framework that already had the implementation of the neural network. Already, is there, it's a framework. And one of the parameters that you're going to select when you create a neuron or a layer is, tell me, which is the equation that you want to use? It's something that you are going to put in the parameter. And you know what? By default, if you didn't put that information, it's going to be that one. But again, it's not the only one. You can select about several different options. The only reason because I am mentioning this equation and I am giving you the example is because I need to tell you, or you need to remember that the equation is very important, and changing the equation can change the output of your neural network. You need to understand this just because later, as a software engineers, you are going to provide a parameter, and that parameter is going to tell the framework which equation to use, and that equation is important. Good news, there is a book. I am going to give you this table. And in the table is, okay, equation name and what is good for. Software engineers, the only thing that you need to know is what I am doing. Recognition of dog and cats. This is the equation that is good to use. Wait. I would like to improve the recognitions of dog and cats in pictures. You can create your own equation, but creating your own equation is more computer science oriented. Here, software engineering, these are the questions that already exist in this particular framework. Which one you select? Knowing that. Clear. Good. So addition, normalization, two things that are going to happen. And from the inputs, you get an output. Tell me, what do you think is the meaning of the output? Because as far as I have tell you, it's going to be a value between 0 and 1. What is usually computer science, math, the meaning of a value between 0 and 1?
Possibility of the answer.
Yes. It's a probability. So are you telling me that you're going to put all the input? Are you going to apply addition and this equation that you show me? And you're going to get as an output a number 0, 1, that is basically 0 is no, 1 is yes, and in the middle you have the probability. This one is 73% of probability. 73% of probability of what? Depending on your data, if I give you the grades of my students and the attendance of my students, maybe that output is the probability of my student to pass the class or not. Or if you want to do the opposite, the probability for the student to fail. Are you telling me that the output, one neuron, is basically going to tell me yes or no about something? What if I want more answers? What if I want yes or no for more than one question? Put more nodes in your output. Each node is going to tell you kind of yes, no probability for one particular thing. Makes sense? Okay, this is the input, this is the output, but the most important thing is how that equation, addition, and this crazy thing, normalization with the equation, is going to solve the problem of classifying my students, or is going to solve the problem of recognizing something in a picture. We need to make that connection, right? We continue next lecture. Thank you.